Let's look at two-dimensional motion in a gravitational field. We'll consider an object that's moving in a plane. We'll have a horizontal x-axis and we'll have a vertical y-axis. And the only thing that it's subject to is the force of gravity. So the acceleration is 0 minus g, where g stands for gravity. Now, we're also told that the initial velocity will be u naught v naught, so that's the velocity when t equal to 0, and the initial position when t equals 0 is x naught y naught. We want to find an expression for the velocity and the position vector. Well, first, if we have the acceleration and we want the velocity, we know that the velocity will just be the antiderivative of the acceleration. The antiderivative of the vector 0 minus g will be 0 minus gt. I'm just finding the antiderivative for each of the components, plus some constant c1, c2. So that means that v of t is equal to c1, comma, c2 minus gt. But we know that the initial velocity, v of 0, is u naught v naught. So plugging in t equal to 0, we get v naught on the left, which is u naught v naught, equal c1 c2. Again, I'm putting in 0 for the t on both sides. That means that c1 is u naught and c2 is v naught. So that means our velocity vector, v of t, is u naught, comma, and I'm going to rearrange these. It'll be v naught minus gt, but I'm going to write it as minus gt plus v naught. So that's our velocity vector, and that's exactly what this says here. Now let's find the position vector. If we have the velocity vector and we want the position vector, we need to integrate again. So r of t will be the integral of u naught minus gt plus v naught with respect to t. But that's just u naught t minus g t squared over 2 plus v naught t plus some constant vector. I'll call this one k1 and k2. Well, that means then that r of t is equal to u naught t plus k1 and then minus gt squared over 2 plus v naught t plus k2. Now r of 0, we're told, is equal to x naught y naught. But plugging in 0 on both sides will give us k1, k2. So that means k1 is x naught and k2 is y naught. So that means r of t is u naught t plus x naught minus gt squared over 2 plus v naught t plus y naught. And that's exactly what we have here. So given that the only thing acting on this object, the only gravitational force is gravity, then we can find what the velocity and the position vector are for these functions. Okay, so now let's say a baseball's hit from 3 feet above home plate with an initial velocity of v of 0 equal to 80. So we're told that the u naught is 80 and the v naught is 80. That's actually the horizontal and the vertical components of that velocity. Now what they're telling us by saying that the ball is hit 3 feet above home plate is they're giving us an initial position. They're telling us that R of 0, 3 feet above home plate, the X component would be 0 and the Y component would be 3. So now we have our initial conditions for V naught and R naught. We want the position and the velocity of the ball between the time it's hit and the time it first hits the ground. So we want functions of t. Well, we know that V of t is given by the u naught and then the minus gt plus v naught. And we'll have also that the r of t is u naught t plus the x naught, and then minus g over 2 t squared plus v naught t plus the y naught. So those are the functions that we just derived. So plugging in your initial conditions, we have that v of t is 80, and then minus, well, let's go ahead and use the fact that gravity is 32 feet per second squared, since we're referring to 3 feet for our initial condition. So we'll have negative 32 over 2 t squared, oops, t, I'm doing velocity, so minus 32t plus 80. Just putting g for 32 in here, and then v naught and u naught are both 80. Okay, r of t will be 80t plus x naught, but our x naught up here was 0. And then minus 32 over 2, so minus 16t squared plus 80t plus 3. And that's our position function. So that gives us the position and the velocity for any time between when it was hit and when it hits the ground. We want to show the trajectory of the ball as actually a part of a parabola. Now to do that, we're going to take the two equations and try to eliminate the variable t. Now look at your position function, r of t, which is made up of your x of t and your y of t. Now we'll recognize a parabola when we see it in terms of x's and y's. So we know that x is 80t, and we know that y is negative 16t squared plus 80t plus 3. So changing t equal to x over 80, then we get y equal negative 16 x over 80 squared plus 80 times x over 80 plus 3. That simplifies to y equal negative x squared over 400 plus x plus 3. And that's definitely an equation of a parabola. Now let's look at part 3. Assume that you have a flat playing field. How far does the ball travel horizontally? To determine how far it travels horizontally, we want to know when it actually hits the ground. Well, one thing good about working with these motions is that you're able to look at the x value, the horizontal distances, and the vertical distances separately. So if we want to know how far the ball travels horizontally, we want to know at what point the y is equal to 0. So now take the equation that we have for the y component, which is this right here, and just set the y component 0. So if y is equal to 0, then we want to solve negative 16t squared plus 80t plus 3 equal to 0. Now, this isn't going to factor, but using the quadratic formula, t equal negative 80 plus or minus the square root of the b squared, 6400, minus 4 times negative 16 times 3, so that'll be plus 192, all over 2 times the a. That comes out to be negative 0.04 and 5.04. Now, the negative 0.04 doesn't make any sense since we're talking about t being time. So the time would be at t equal 5.04. So how far does it travel? We want to know the horizontal distance. So that's the x value. So x, when t equal 5.04, x is equal to 80 times t, which is approximately 403 feet. So now we have the distance that the ball travels horizontally. So we wanted to find the x value, but we wanted to do it at the point where the y value was 0. Okay, now plotting the trajectory, we can just simply plot this equation, and you can do that using a calculator. We want the maximum height of the ball now. Well, the maximum height will be the largest y value. You can get that by taking that parabola's equation and determining what the highest point will be. Another way to do it, using the fact that we're doing the velocity and the position separately here, is to find out when the velocity is actually 0. Now, which part of the velocity? Now, are you talking about the horizontal component of the velocity or the vertical component? If we're talking about the maximum height, that means that the height will be at a maximum there, which means that the y component of the velocity, the vertical component of the velocity, should be at its highest. So what we want to find then is when there's no more increase in the vertical for the velocity. So let's take the y component of the velocity function, which describes the vertical component of that velocity, and find out when it's 0. So negative 32t plus 80 equal to 0. So the velocity in the upward direction is 0. That means then that the t is 80 over 32, which is 40 over 16, which would be 20 over 8, 10 over 4, or 5 halves. 16 goes into both of them. So at 5 halves is when we will actually have the greatest height. So to find that greatest height, now we're looking for what the y value is at the position. So the greatest height is given by the negative 16t squared plus 80t plus 3, and just evaluate that at 5 halves. And that comes out to be 103 feet. Now, does the ball clear a 20-foot fence that's 380 feet from home plate? Okay, so we're talking about the distance from home plate. That's a horizontal distance. So this will be an x value. So when that position function has that x value, which means that our x value of our position function, 80t, will be 380. That means t is equal to 19 over 4. That's the point in time when the ball will be 380 feet out from home plate. So what we want to determine then is what is the height of the ball at that point. Now the height of the ball is the y value for our position function. So find negative 16 times 19 over 4 squared plus 80, 19 over 4 plus 3, and that comes out to be 22 feet. So if the fence is 20 feet at a distance 380 feet from home plate, we see now that the ball's height will be 22 feet. So it will clear the fence 380 feet from home plate. Now here's some other formulas that might be useful. Assuming that the object's traveling over horizontal ground and that gravity is the only force acting on it, and the initial condition is actually 0, 0, and the initial velocity is given by v naught cosine alpha, v naught sine of alpha. So what we're assuming here is that we're actually shooting an object at an angle alpha from a horizontal. So we've got an angle that's being given when the object is actually being hit. So if you want to determine the time of the flight, the time can be given by this formula. The range, which is how far it will actually travel, will be given by this, and the maximum height will be given by this. So if you have some problems that are asking these type of questions, now this is assuming that an object is hit at an initial velocity, u naught v naught, and that it's at an angle made with the horizontal. So it's just another example where we're just given different information and we're using the same techniques to actually develop these formulas. So you can just use these formulas if you have questions relating to those.